Hello friends, welcome to this Fredholm integral equation calculus of variation and its application lecture, and in today's lecture we are going to discuss the solution of Fredholm integral equation with the help of iterative methods, or we can say that method of successive approximation. So if you look at here, Fredholm integral equation of second kind, I can write it here, y of x equal to f of x plus here we have k of xt and y of t dt here. I am not writing any limit here, because if I write a to b, then it is your Fredholm integral equation, but if I write the upper limit as function this x, then it is known as Volterra integral equation of second kind. But whatever we are going to discuss today is equally applicable for both the kind of equation, means for Fredholm integral equation as well as for Volterra integral equation. So here I'm going to discuss this with the Fredholm integral equation, and at the end we are going to discuss for Volterra integral equation also. So let us look at the theorem here. So first theorem to solve this is this. So here we are assuming that we have a Fredholm integral equation of the second kind is given as y of x equal to f of x plus lambda times a to b kxt yt dt. I am putting lambda just to consider the eigenvalues and eigenfunction problem also. So here we are assuming that this kernel xt is non-zero and is real and continuous for all values of x and t in this interval ab, and also we are assuming that this kxt is bounded by this capital M for all values of x and t in this interval ab. Also that this small function f of x is again non-zero, real and continuous for all values of x in ab, and here f of x is also bounded by, say, this is small m, and for every x in this interval ab. So and here we are assuming that this lambda, which is a constant here, is satisfying this condition that mod of lambda is bounded by this quantity 1 upon m b minus a, where m is the bound of kxt, is it okay? So in this condition we will show that our Fredholm integral equation 1 is having a unique solution in the interval ab, and it is given by this series, infinite series, which is absolutely and uniformly convergent series. So if you look at here, it is a series given in terms of lambda. So if you look at this is how to prove it, let us try to prove it here. So this proof is based on a very simple idea. The idea is this, that if you look at this is the equation here. So since I am discussing right now Fredholm, so I am just using the upper limit as b here. So if you look at y of x is given as this thing. Now problem is that this is yt, which is unknown function, so we cannot say that this is a solution here. But if I assume that if I know what is yt here, then we can find out the solution. So how to get how to do this kind of integration? If I can do this integration, we are done, but this is quite difficult here because yt is still unknown to us. So what we try to do here, we can write it here as f of x plus this lambda is missing here, lambda a to b here and k of xt, and here in place of yt let us use this formula again. So we know that yt yx is a function which satisfies this Fredholm integral equation. So I can use this expression for this yt also. So it means that I am writing here yt, let me put the what is the yt here, I can write it here f of t here plus lambda times a to b. Now here I have to write it k of t. If I am using in place of x I am using t, then I have to use some other variable here. So let us use t1 here and y of t1 here and d of t1, right, and this is d of t. So what we have done here, we have say find out the value of yt with the help of this integral equation itself. So here how we have done here, we have written here y of t in place, and we are just changing the value x here by t. So it is f of t plus lambda times a to b. I am using x by t, replacing x by t. So this variable t, integration variable, I am writing as t1 and y of t1 and dt. Okay, so it means I can write it like this, and if you simplify this further, you will get what? This is what y of x is given as f of x plus lambda times a to b. I am just multiplying this, so it is what? K of xt f of t dt plus, if you look at the second term is going to be lambda square a to b k of x of t integral a to b k of t t1 and y of t1 dt1 and d of t. Okay. So now this process we can keep on doing. So it means that here also, if you look at, if we use the same first equation for y of t1, you can find out what is the value of y of t1, put it here, and we can go to the next step. So this is we can keep on doing. So if you look at, it is written here. So here we know that Fredholm integral equation of is given as this. Then if we find out the value of y of t1 here, then it is y of t like this. Then if you put it here, we have y equal to f of x plus lambda times a to b kxt ft dt plus lambda square a to b kxt a to b kt t1 yt1 dt1 dt, which we have shown just now. Okay, so it means that yx is given by this equation number 8. Now if I do the thing again, it means that if we want to find out the value yt1 here, so if I want to replace this yt1 by the value given here, then it is basically what? Let me write it yt1 here first. So y of t1 is basically f of t1 here plus lambda times a to b, and I am writing here k of t1, and let us change this integral variable by say t2 and y of t2 and d of t2. So what we try to do here, we use the Fredholm integral equation which is already given, and find out the value of y of t1 here in terms of y of t2 and put it here. Then if you put it here, then we have another term given, another term we can add, and we can write it like y of x equal to f of x plus lambda a to b kxt ft dt plus lambda square a to b kxt a to b k tt1 ft1 dt1 dt, which we have obtained in a previous iteration also, plus there is one more term added here, lambda cube a to b kxt a to b k tt1 a to b k t1 t2 yt2 dt2 dt1 and dt. This is triple integration basically. So if you proceed in this way, we can write our solution in this series y of x equal to f of x plus lambda times a to b kxt ft dt plus lambda square this term and so on. So this series will having this remainder term Rn plus 1x, which is given by this. So what we can do here, if we keep on doing this, then we can get a infinite series in terms of lambda for this y of x. So we can say that the solution of Fredholm integral equation is given by this y of x equal to f of x plus these many terms, provided that this series is convergent and this Rn plus 1x is tending to 0. So for that let us look at this following infinite series fx plus lambda a to b kxt ft dt and so on. We want to show that this series is convergent series. For that we will utilize the assumption we have assumed earlier. What we have assumed earlier is that this kernel kxt is continuous function and bounded in this interval a to b for values of x and t in interval a to b, and this fx is also continuous and bounded in this interval a to b. So for that, let us consider the nth term of this infinite series, call it Snx, and Snx is given by this. Now here what we try to do here, we just try to find out say bound of this Snx. So if you look at here, modulus of Snx is given by this. Now here if you look at this term, this k tn minus 2 tn minus 1 and f tn minus 1. So this f small f tn minus 1 is bounded by small m. So I can take that upper bound here, and if you look at this, this is bounded by k xt is bounded by capital M here. So I can write that this small m is taken out and capital M for this term and every term here. If you look at here, each t, t1, t2, x, everything is lying in this interval a to b. So it means that I can utilize the upper bound of kxt, and which is given by capital M. So here we have n times of integration. So we have m to power n outside, and upper bound of this, that is small m here, lambda to power n is already there, and then we have constant integral a to b dt n minus 1 n-fold integration basically. So if you do this integration, we will get this b minus a to power n here. So I can say that this nth term is bounded by lambda to power n, m, small m, capital N to power n, b minus a to power n. So it means that I can write it here like this. I can say that your series f of x plus I can write it here summation your lambda to power I here from 1 to infinity, and here we have expression, we have ith term here, and it is I-fold integration is given here, and we say that this is Si, and this is bounded by, just now we have calculated, this is that modulus of lambda to power I and small m, capital M to power I, p minus a to power I. So I can say that if you take the absolute value here, then this is going to be bounded by modulus of f of x plus summation I equal to 1 to infinity, and here I am writing here a modulus of lambda to power I, small m, capital M, I, b minus a to power I. So I can say that this is a geometric series with the common ratio lambda capital M, b minus a. So basically this is a geometric series, and this geometric series will converge provided this quantity is going to be less than 1. So it means that this series is convergent, and every term, ith term of this is less than or equal to ith term of this. So by Weierstrass-Hammond test, we can say that this series is not only convergent, it is uniformly convergent, and the benefit of uniformly convergence is that we have, if you look at the each term is continuous here. So if you look at here, this fx is continuous, this is continuous, so every term is continuous function. So we can say that this is an infinite series of continuous function. So your limit is also going to be a continuous solution. So it means that whatever be the limit, that is going to be a continuous function of x. Okay. So here this series will converge only when modulus of lambda m b minus a is less than 1, and this convergence is absolute convergence and uniformly convergence, and in this case we can assign that value as y of x here, and y of x is continuous because of this uniform convergence, and if I assume that it has a maximum value, if we call this as maximum values as capital N, then we can say that the remainder term which is given by equation number 13, this is term ytn. So this is capital N taken out, and this is n kxt is coming in n plus n terms, n plus 1 times. So we have that bound of Rn plus 1 is given as modulus of lambda n plus 1 n times capital M to power n plus 1 b minus a to power n plus 1. So here we already know that this modulus of lambda capital M b minus a is less than 1. So as n tending to infinity, this is also going to be 0. Let me write it here. We have Rn plus 1 modulus of this is bounded by lambda capital M b minus a here, modulus lambda here, to power n plus 1, and this is n, which is a bound of yt, and as n tending to infinity, so this term is tending to 0 because this is already less than 1. So we can say that, I hope here it is modulus of lambda. Okay. So here we can say that this series is convergent, and your solution y of x is given by this infinite series, provided that lambda is a constant which we have taken here is satisfying the condition. Let me look at here. So it means that this Fredholm integral equation will have a series solution which is uniformly convergent, provided that first condition, second condition, and modulus of lambda is less than 1 upon m b minus a, this condition hold. So here we have a theorem for Fredholm integral equation. If you look at here, the same thing we can do for Volterra integral equation. The only difference between Volterra integral equation and Fredholm integral equation is that the upper limit is replaced by x here, variable x here. So let us look at the same thing for Volterra integral equation. So yx is given here f of x plus lambda times a to x k of x of t f y of t here, y of t dt here. So here we are assuming the same condition. What condition we are assuming? Here we are assuming that kernel is real and continuous for all values of x and t in AB, and having bound capital M, which is the upper bound of this modulus of kxt, and this small f of fx is also real and continuous and satisfying this bound. The third condition which we have assumed for the case of Fredholm integral equation is not required for Volterra integral equation. Here we can simply say that lambda is a constant, so I can replace this third condition by the third dash, which says that lambda is a constant. So here no need of any condition for this lambda. The reason being that if you look at what we have done here, we have started with the first substitution, writing this f of x plus lambda times a to b here. If you write it here, k of xt kx comma t, ax comma t here, I am writing the value yt here, which is given by this only. So f of t plus lambda times a to x here, and if you write it here, I am writing t t1 y of t1 and dt1 and dt here. So if you look at, this is same as the previous thing, and we can write it here, f of x plus lambda times a to b k of xt f of t dt plus lambda square times oh sorry, here it is not b, it is x here, sorry. So this is x plus lambda times a to x k xt and integral a to x k of t t1 y of t1 dt1 and dt here. So if you look at here also, we have not it is the same procedure which we have adopted for Fredholm integral equation, and in this way we can again write down the expression for y of t1 using the same equation here and keep on this procedure. So if you look at, we can repeatedly we can go up to say this thing. We can write down y of x equal to f of x plus lambda a to, now here all these b's are replaced by your variable x. So you can say that for in case of Volterine integral equation, your solution y of x is given as f of x plus lambda a to x kxt ft dt plus lambda square a to x kxt a to x kt t1 ft1 dt dt1 dt and so on. Similarly, we have Rn plus 1 given by this n plus 1 times fold integration lambda n plus 1, upper limit is simply replaced by this x. So there is no change other than that this b is replaced by the variable x. So we can similarly say that this series, in this way we can as n tending to infinity, this is going to be an infinite series. So we say that this is the infinite series, and we want to claim that the solution of Volterine integral equation y of x is given as this infinite series. So what we need to prove here, that this infinite series basically converge. So converge. So here also look at the nth term of this infinite series. So Snx is given by this term, only thing is that upper limit is replaced by x here. So when we use the condition that kxt is bounded by capital M and your f of x is bounded by small m, we can write down this capital small m term outside, capital M term outside, modulus of lambda to power n is already there. The only thing here change is this. Let me write this expression for Snx. So Snx is going to be lambda to power n a to x here kxt a to x here kt t1 and so on a to x k t n minus 2 t n minus 1 f t n minus 1 dt n minus 1 and up to dt. So it is nth integration. So modulus of Snx is going to be is less than or equal to modulus of lambda to power n. Now this is bounded by small m, I am writing here, and kxt is bounded by capital N, so it is n times, so we have m to power n, and this is the left here a to x and so on a to x and dt n minus 1 dt n minus 2 and so on and dt1 and dt. So this thing is left here. If you look at here, if you solve the inner one, this is basically what you can write it here as the first one is x minus a, this one. Now next if you integrate it, you will get what? You will get x minus a whole square upon factorial upon 2. So it means that I can write it here, this is x minus a, and if you integrate further you will get x minus a square upon 2 here, and if you further integrate you will get x minus a cube and 2 3, which I can write this as I can write it here this as x minus a to power 3 divided by factorial 3. So if you use this notation, then this is going to be written as x minus a to power n divided by factorial n. So here in this Volterine integral equation, your mod of Snx is replaced by bounded by mod of lambda to power n, small m, capital M, n, and x minus a to power n divided by factorial n, and we already know that x is lying between this a to b here. I can take I can include this endpoint also. Then I can say that this is further bounded by modulus of lambda to power n, small m, capital N, and b minus a to power n upon factorial n. If you remember, the only difference here is this denominator, that is factorial n. So in Theorem integral equation we have only this part, but in Volterra integral equation, because of the upper limit is variable, we have this factor coming out, that is factorial n, and this is factorial n is a very very fast going to infinity as n tending to infinity. So I can say that if I take limit n tending to infinity, modulus of Sn x is less than or equal to limit n tending to infinity. I really do not care because this is anything but polynomial, and because of this factorial n, it is very rapidly going to 0. So we can say that modulus of lambda to power n small m capital N b minus a to power n upon factorial n. So because of this term, this is tending to 0 whatever lambda is. So we can say that in case of Volterra integral equation, your Snx nth term of this infinite series is tending to 0 without any condition on lambda n, right. As n tending to infinity, your solution is going to be going to be represented by equation number 14 here. Only thing is b is replaced by x. Now if you look at the remainder term is again you can use the same theory available here, but here again if we say that solution is given by the previous series, we can say that again this convergence is absolute and uniformly convergence. So your solution is yx is going to be continuous in this interval a b, and we assume that the solution yx is bounded by capital N, and in the same way we can find out say bound of this. Again here we have the same change here. So here also we can have the upper bound of Rn plus 1 is this. So here we have modulus of Rn plus 1 x is bounded by modulus of lambda to power n plus 1 capital N here, upper bound of yx here, m to power n plus 1 here, b minus a to power n plus 1, and divided by factorial n plus 1. So again here as n tending to infinity, this term tend to infinity very fast, and which makes this Rn plus 1 x tending to 0 as n tending to infinity. So we can say that here also we will get a power series in terms of lambda as a solution for y of x, and here we do not have any condition on this lambda. In Theorem integral equation we have a condition lambda, but here for Volterra integral equation we do not have any condition on y of x. For every lambda it will converge. Okay, so in next lecture we will discuss the approximation method to solve Volterra and Theorem integral equation. Thank you for listening us. Thank you.